derivatives and the gradient vector. Okay. Suppose we're at Reno, right? We went to Reno to get some, we felt lucky. Hope we were make some money off some casinos, and Vegas is too big for us, so we went to a little town Reno. Okay. And let's suppose we took a direction, call it go east. So we went east on this. Okay. Or, what if we want to go north? Yeah, let's go north instead. Okay. Now, what's happening here and all of these curves here is 60, 70, 60, 70, 80, so forth, right? These are temperatures. Okay. So what we're saying is, according to our vectors, is that if we take let's say tx, the tangent vector or the partial derivative at Reno, and we're going east. Okay, so like we went that way, so we'll call this t of x. And again, like we said, we went north, right? So let's suppose we say ty. So we'll say let's say ty at Reno going north. This is ty. Now remember, tx and ty are both tangent vectors, right? So they're the rate of change. And we talked about level curves last time. So notice this whole level curve here is 60. So the temperature is changing depending on where we go, right? Which makes sense, right? We go cooler or hotter. Right? We live in California, so everything goes in, how it could go. But the problem is, we can only go left, right, up, or down, right? So we only learned of tangent vectors going this way, this way, this way, or that way, right? So in other words, north, east, south, west. So the question now is, what if I want to go, let's say, what's a good direction? Southwest. South, we want to go this way. Let's call that TZ. Okay. So if we want to go southwest, how do we find that? Right. Because again, look, we've only been able to do vectors that are perpendicular to each other. So, right. But how do we do like opposites? So now we go this way. So we go from 1 degree to another degree to another degree, right? We go to 3 degrees there instead of just going to 1 degree of up or down or left and right. So that's what we're going to be doing right now. These are called directional derivatives. Okay. So in three-dimensional space, this is actually what's happening here. Okay. So let's suppose we're given a point P on our surface. Okay. Now we can find the tangent line at that same place, just like normally we've done, right? And this is our tangent plane here. Or sorry, here's our tangent line. Right, so we can find a tangent line and we can find a tangent plane. So that's what this one here is. Now, this tangent plane, however, is very particular. Okay, so this plane is in the direction I want to go in, according to the tangent line. Okay, now this one down here, in this direction there, is parallel to the tangent plane, and this is the directional of a unit vector. So we have three things happening. we have a point, we have a point, the tangent line that's parallel to what we go to. We have a tangent plane that cuts it through it, and we have a unit vector going all in the same direction itself. Okay. And that is what dictates how we want to go by. Okay. So this is the whole thing we want to deal with, because the unit vector itself is going to be our direction we want to go in. That's going to dictate all of these three things happening: where the tangent line is going, tangent plane is going, as that unit vector changes. And just like everything else, given a particular point, meaning going down here, right, it be transforms in the xy plane. I can now alternate how I want to do it. So if I want to go this way, I make a unit vector going that way, and therefore going up, I get a tangent line going this way, and the tangent plane through it. So a lot of things happening to find just going to one particular way besides going north, east, south, and west. But we define our directional derivative as this. So the directional derivative of f at the point xy in the direction of the unit vector AB is given by this. Now, again, don't worry. When we talk about limits, we talk about the derivative, so we do the actual derivative, right? So our normal derivative, our directional derivative called du of f, signify d for direction, with respect to the unit vector u, is given to be this equation right here. So it's the partial derivative of x and y at the point A and B times A plus times B, respectively. And again, this tells us any direction we want to go now, not just up, down, left, and right. So now we can go diagonals. But again, the key thing is we have to find the unit vector. So let's try a couple examples out to illustrate exactly what we're about to do. Now, if we're positioned at the positive x-axis, so in other words, if this point is reflected actually on the x-axis here, like right here, or anywhere on here, and we make the line, we have an angle that makes it from the origin. Let's call it theta, right? As you can see, right, if I just move it this way, the angle will change depending on what we want. So therefore, our true actual directional derivative looks like this, because the angle it makes does actually change, right? I can go all the way around now, however I want, 360 degrees, just like we can walk how far we want in any direction, given a specific angle. Now, again, that kind of makes sense, right? Cosine is always the x term, and sine is always the y, because, they're associated with the x and y coordinates themselves. All right, so now that we have our actual directional derivative, let's do a couple examples. So find the directional derivative if fy is equal to this function, and it gives us the unit vector. So with the given unit vector of, so given to be an angle of pi over 6, and we want to find the direction derivative of 1, 2. All right. Okay. So first off, we got to find these partials. So partial derivative with respect to x. And then the partial derivative with respect to y. Yep. All right, so we got that down. So now we plug it into our formula. So the directional derivative is going to be, according to our equation, this. Times cosine theta plus this. Times sine theta. And now all I do is plug in cosine or pi over 6 for cosine and sine, and we get our answer. And then we also plug in the point 1, 2. So x is 1, y is 2 into our directional derivative. And let's see what we get out. So 1 squared is, so it's going to be 3, minus 3 times 2 is 6. And cosine of pi over 6 is radical 3 over 2. Plug in 1, get -3. Plug in 2, that gives us 16. And sine of pi over 6 should give us 1/2. So this ends up being -3, rather than 3 equals 2. This is, what is that, 13? Yeah, 13 over 2. So putting these together, there's our directional derivative at the point. So remember, this is our rate of change in that particular direction. Okay. So what if the angle is not given to me and we have to use the old definition to do so? So find the directional derivative of this function with the unit vector 2i minus 1j at the point 0, 1, 1. So same thing, got to find the partials with respect to x and y. So this is going to be 3x squared minus 3y. Oh, it's the same ones, I forgot. So respect to y, it would look familiar. There you go. Now this time our unit vector is 2, -1. Or in general, because we have 3 terms, 0, because we have the k value there, right? So 2, -1, and 0 because we have the k value, and we're in 3 dimensions. Okay. So now, according to our equation, our directional derivative with respect of f is going to be this times the a value. So this is a, b, and c. A plus b. And now we're going to plug in a and b, and then x and y respectively are supposed to be. So remember, here's our point. So x is going to be 0, and y is going to be 1. Okay. So what do we get? So x is 0, so that goes away. So we just get -3, and a is 2, plus x is 0, so that goes away. We just get 8, -1. So we get -14. That's the rate of change in that direction of the point. So now that we know direction derivatives, we define something that's very important to multivariate calculus, and it's something we've already done before. Now we're just going to call it an actual name, is the gradient vector. So the gradient vector is a function of 2 or more variables, x, y, and z. And then the gradient of the vector, denoted as like the opposite delta of f, is just defined to be the vector of the partial derivatives. That's all it is. Okay. So whenever we want to find the gradient, it is just the partial derivative with respect to each variable, and it's in vector format. That's all it is. Okay. And you'll see why, things get a lot easier to look at just based off this information, because now that way, if we apply these into two definitions to our directional derivative, our directional derivative literally now looks like that. Right? Like everything else in math, make it simpler to look at, right? May not be as simple to actually do, but it's simple to look at. So our directional derivative can be written as this. Now, if you're wondering why that makes sense, well, let's find out. So this is our general definition. Right? We just talked about it. Well, isn't this the same thing as the dot product? Right? Dot product means we just multiply components and add them together. That's the same thing. If this is a vector, we know this is a unit vector. And therefore, this is now the gradient of f. It's a nice little proof. Okay. So that's what we can actually write it into that format. Okay. All right, so in that case, more examples. So now find the rate of change of the function at the point 1, -2 in the direction of the vector b equals 2i plus 3j. Okay, now remember, rate of change means directional derivative, right? Find the direction, find the rate of change. They all mean the same thing. In other words, if you're not sure, always just find the derivative. Rate of change is always going to be derivative in our case, right? And it's always been that way. Okay, so find the derivative. So basically, find the gradient. That's what we're looking for, right? That's what we want, the gradient of each one. So derivative of f would be just 2x y to the fifth minus 4y. And with respect to y would be 5y to the fourth x squared minus 4x. So our gradient vector is going to be those two put together. Now we want it at the point 1, -2. So we can find a gradient at the point 1, -2. Just plug it in, 1, -2 in here. Okay. So if I did my math correctly, I should get this. And since we want the directional derivative of f, so we have our gradient, and our unit vector is going to be, well, it's v, right? So it's v, 2, 3. So this is going to be -56 times 2 plus 76 times 3, according to our definition, right, which is right there. Which gives us 116. So that is the rate of change of this function at the point 1, -2 in the direction of that unit vector, or of that vector. So let's try a little bit more practice. So find the rate of change of the function fy is equal to x sine, and this is parentheses, sine of yz in there, at the point 1, 3, 0 in the direction of our vector there. So same template we had above. Okay. All right, so first off, we got to find a gradient. So first, with respect to x only, so it's just going to be all of this. Next is respect to y. So remember, this is actually a chain rule property. So derivative of the inside times the derivative of the outside. So derivative of the inside with respect to y is just going to be z. And the derivative of the outside is just going to be x on the outside. And the derivative sine is going to be cosine. And then in respect to z is the same process. Derivative of the inside is just going to be y. And the outside is going to be again cosine. There we go. So there's our gradient vector. And now we want at the points 1, 3, 0. So remember, this is going to be x, y, and z. So in between sine is going to be 0. Sine of 0 is 0. That's nice. Since z is 0, that all goes away. Wow, okay. And so let's see here. So cosine of 0 is 1. And 1 times 1 is 1. And 1 times 3 is 3. So this is just the vector 0, 0, 3. Our unit vector is 2, 2, negative 1. And now, because we have 3 dimensions, just like we have definition, our directional derivative is going to be 0 times 2 plus 0 times 2 plus 3 times negative 1, which gives us just negative 3. So the rate of change of our function at the point 1, 3, 0 in the direction of the vector is negative 3. Questions there at all? Okay. So now I have a dilemma. Now, what if these two functions were the same? Or we had a question like that earlier, and we had different answers. Question is now, if I chose a different point, let's say from this question, what would that directional derivative be? Okay, so we could do that. But what if I want to find the fastest rate of change or the slowest rate of change? Do I have to pick every possible point on the surface and figure it out? Right, that's our dilemma now. So now the question is, so how do I figure out the fastest rate of change of the fractional directional derivative or the slowest directional derivative, respectively? Okay, so that's what we're going to find out right now. So if we were to find all possible directional derivatives, which one would be the fastest? In other words, the maximum of the function f. So the good thing is we can actually find it. So if f is the directional derivative of 2 or more variables, the maximum value of the directional derivative, so du of f, is the see if we remember that, is the distance of the directional derivative at this, and this occurs when the unit vector, this is the key thing, when the unit vector u has the same direction as the gradient vector. That's an interesting part. Okay, and that's a key thing we got to figure out. Is a unit vector in the same direction as the gradient vector? Because if it's so, therefore that is the maximum rate of change going in one direction at that particular point. Okay. All right, so let's try this question out. So I'm going to change this up a little bit. So given our function f of y, f of xy to be y equals y to the e dx. We want to find the rate of change at the point now p of 0, 2 in the direction of PQ, where, and I'm going to change this up again, Q is the point 2, negative 1/2. And then part B is, in what direction does the function have the maximum rate of change? And what is the maximum rate of change? Okay. So first, we're just going to find the rate of change of from here to there. That's all we're going to do. Okay. So first off, we need to find our gradient vector. All right, so with respect to x itself, it's just going to be y e to the x. With respect to y, just e to the x. That's kind of nice derivative. Next, we have to find our vector. Well, let's see. So in order to find a vector, we'll call that vector PQ. We go from here to there. So 2 minus 0 is 2. And then negative 1/2 minus 2 gives us negative 2 and 1/2, or I'll put it in fraction format. That's going to be 3 over 2. Okay, so we got the vector portion of that portion of that. Now we can plug it in. So our directional derivative is going to be our point, yeah, is x and y. So I'll just do the general one for now. And then just plug in 0 and 2 for x and y. So e to the 0 is just always 1. So this is just going to be 2, 2, and then 1 times negative 2/3. So 4. So this gives us what here? 8 over 2. So 5/2. Okay. Now, so that's part A. Now, part B says, in what direction does the function have the maximum rate of change, and what is the maximum rate of change? Okay, so remember, this is only good for if the unit vector is in the same direction, and that's the key thing. So first, we got to find the unit vector respective with B, or unit vector respect to this. So the unit vector is, if you guys remember, it's going to be, well, it's a couple things, right? It is that. So first we got to find the magnitude of it. So this will be 4. And this is going to be 9/4. So 16 plus 9, 25 over 4. So 5/2. Right, so then it's going to be, the unit vector is going to be let's see, so this stays the same, we flip. So 1/5. That. Okay, so now let's go back to our definition here. So it says the maximum value of the directional derivative is the magnitude of the derivative the magnitude of the gradient vector, and it has to occur in the same direction of the gradient. Okay, so what does that really mean? So this is saying if this unit vector, right, this is the unit vector we got from this point, but in general, this unit vector has to be the same direction as the gradient at the point P. Okay. So now if I just go back to my gradient vector, and if I plug in the point 0, 1, so I get 2, 1. So notice the difference between the unit vector at this point and the actual unit vector that would give it the maximum value. Right, so this is a unit vector at this point to see, what it would go by. Here is our actual unit vector we were looking for part B. So all I did this is to see you guys to see the difference between one and the other. Is this is the unit vector would use to be the maximum value itself. And now all we have to do is find the magnitude of f, which is just going to be radical 5, right? 2 squared is 1, 2 squared plus 1 squared gives us that. So the one thing I want to emphasize is to make sure when it comes to part B, or example given, find the maximum rate of change, is you won't actually find the unit vector of the point itself, right? This will I gave you guys an example what this would be like in respect to the actual one here, right? Notice there's a big difference between the unit vector at this point and the general unit vector we're looking for. Remember, and the whole thing is this point, or this unit vector, goes along the lines of this one right there, right? Arbitrary of this point. So only at this point P, where does it actually go to? Okay, so a lot of stuff happening there. Why don't we try another example? All right, suppose the temperature at a point X, Y, Z is given to be T to be all of this, where T is measured in degrees Celsius, X, Y, and Z in meters, in which direction does the temperature increase the fastest at the point 1, 1, -2, and what is the maximum rate of change? Okay, so first we need to find our gradient of T. Okay. Now, just for my sake, I'm just going to rewrite this. Look like that. So now if I take the derivative with respect to each one individual, for me, it looks a little easier. So chain rule again. So derivative the outside is just going to be with respect to X. And then derivative the inside will just be 2x. And I'm just going to go down. It's too much going across. So now with respect to y, it's same as the mimicry of everything else. And then with respect to z. Okay, so now we have that. So now all we're gonna do is plug in the points, 1, 1, -2, in for X, Y, and Z. And hopefully if you believe my math, I get this. That. Okay, so let's go back to the question. So which direction does the temperature increase the fastest at the point 1, 1, -2? And what is the maximum rate of change? Okay, so remember, it's the fastest in this direction, right? Because it's the fastest when the gradient of t is the same direction as the unit vector, right? So this is our fastest right here. So this is our direction at this one. And now, what is the maximum rate of change? All we have to do is find the gradient of t, or sorry, the magnitude of the gradient of t. So all I did was divide these up individually and then square them. And hopefully I did this right. Which gives us, that's approximately that. Good. Questions there at all? Yep. How'd you get 2, 1? Yes. So it is the maximum of, well, as long as the unit vector is in the same direction. That's right. So it's not going to be the same, but it's the same direction of the gradient. So that's why once we find this, the maximum is always at the point itself. That's going to be the fastest direction. Now, if we're given a different unit vector here, then we could find the directional derivative at that unit vector. But if you want to find the maximum, the unit vector is exactly where the gradient is itself. So for example, here, if or instead it said, what is the directional derivative of the unit vector of, let's say, 1, 5, 2? So we'll use 1, 5, 2 to find the directional derivative, right? And then in part B would say, what is the maximum? So we go back to its gradient, plug in the point, and that's guaranteed to be it no matter what. There you go. Hopefully that answers your question. Okay. All right. Let's go back to surfaces real quick before we do something else. So let's suppose we have a surface S, right? We have a nice little surface S. And let's suppose the surface has the equation of x, y, z, some constant k, equals some constant k. And let's suppose we have a point P on the surface. We have a point P right there. Now we have something called level curves. We talked about this already, but we're going to go much more in depth with level curves. So let's suppose a level curve C through P. So we have a curve here, a different color. So we have this curve C going through it. And because we have a curve, so therefore we can find derivatives, tangent planes, all that fun stuff. And in fact, that's what we're about to do right now. Okay. So let me first write some stuff down. So we have a level curve. We'll call that C1 through P. So let's suppose the equation of this level curve is R of T. Okay, so therefore, just like I said earlier, we could find the rate of change, the tangent plane, all that fun stuff at that point. So first, let's find the slope. So then the slope, which is just the same as our tangent slope, gives us that. Yeah. Now we just talked about this, right? This is just going to give us our gradient. So nothing really brand new here. Yeah. Now, the key thing we want to figure out is the second part of this directional derivative. How do we find the tangent plane that's parallel to the direction we actually want to? Okay. Now remember these tangent planes, and it's kind of hard to see, but this tangent plane is right here. Right? Think of it as like a flat surface just sitting on it itself. Okay. So the question is, how do we find the tangent planes of all possible scenarios given any type of curve using its gradient? That's what kind of we want to figure out itself. So according to our definition now, any tangent plane to a level surface is given to in this situation here. Or in fact, exactly that. It's the gradients of f times the initial point. Okay. Now, here's a key thing, going way back to the very beginning of the class, symmetric equations, okay? So remember, the symmetric equation in our case is going to be called the normal line from now on. So if you remember, symmetric equation is basically this divided by that and equaling each other, right? Those ratios. Okay. So again, just be careful, right? In our case, symmetric equations is now considered normal lines. Okay. But the whole fun part is, how do we find the tangent planes of any arbitrary point now in any arbitrary direction? Because they're going to change depending on the direction we look at. So now that we have a definition, let's try it out. So given the equation x squared over 4 plus y squared plus c squared over 9 equals 3 at the point -2, 1, -3. First, we're going to find the tangent plane. Then we're going to find the normal line. So basically just the symmetric equations. Okay. So now, if you have no idea what you're doing, just find the gradient. That's going to be half the answer already in general, right? Now, it's in this format. This is our f. equals k, so we're good. So now we can find the gradient of it. So this is just going to be, with respect to x, is just going to be 2x over 4. So just going to be x over 2, 2y, and then 2z over 9. Now remember, this is at the point itself. So now we're just going to plug in the point -2, 1, -3. So when we plug this in, so just simplifying, this gives us -1, 2, and 3's cancel, so we just get -2/3. So now our tangent plane is just going to be this. So -1 times x plus 2 plus 2 times y minus 1 minus 2/3 times z plus 3 equals 0. And then for our symmetric equations, or in this case, our normal line, is just going to be x plus 2 over -1 equals all the other relationships. Just our symmetric equations.